In the vast expanse of existence, matter seems solid, reliable, and unmoving. Yet when we look closer, down to the level of atoms, the illusion begins to dissolve. The smallest building blocks of the universe are not tiny bricks of matter, but restless patterns of motion, dynamic and fluctuating. The atom is mostly empty space, with its particles flickering, shifting, and vibrating in endless motion. Beyond that, the deeper question emerges: are these particles truly solid objects at all, or are they nothing more than vibrations of energy resonating in hidden fields? To uncover the truth, we must peel back the layers of reality itself, from quantum mechanics to cosmic fields, and question what matter really is. With that said, let us begin. At first glance, the universe feels firm, dependable, and made of tangible matter. A rock resists our touch, a table supports weight, and mountains stand immovable for ages. Yet the closer we zoom into the fabric of these familiar structures, the more deceptive this solidity becomes. An atom, the supposed building block of everything, reveals itself as an intricate balance of emptiness and movement. If the nucleus of an atom were the size of a marble, its electrons would orbit at distances comparable to a football field. What appears as solid matter is in truth a vast sea of emptiness, held together by invisible forces. This empty architecture challenges the intuition that matter is something. Instead, the solidity we experience is born from electromagnetic repulsion between the electrons of our bodies and the surfaces we touch. Atoms never truly collide, their energy fields resist one another, creating the sensation of firmness. In this sense, what feels solid is not compact substance, but rather energy fields dancing at scales beyond perception. But there is more. Even within this empty design, atoms are restless. Electrons are not stationary orbs but wave-like clouds of probability, endlessly vibrating with quantum fluctuations. The nucleus itself trembles, with protons and neutrons locked in a ceaseless dance dictated by the strong nuclear force. Matter, when stripped to its foundation, is revealed not as fixed particles but as activity, motion sustained by fields of energy. If solidity is only an emergent experience, then atoms are less like bricks and more like resonances in an unseen orchestra. This realization shifts the question from what matter is to what energy patterns underlie it. At the quantum scale, vibrations are not mere metaphors, they are the very fabric of existence. The smallest scales of reality are not silent but alive with motion, a constant trembling known as quantum fluctuations. Even in a perfect vacuum, where no particles are thought to exist, energy hums in invisible fields, creating virtual particles that flash into and out of existence in unimaginably short intervals. This restless activity hints at a profound truth: the universe is never still. Electrons, often imagined as tiny balls, instead behave like waves, spreading across space in patterns of probability. These wave functions resonate, interfere, and vibrate according to the principles of quantum mechanics. The shapes of these vibrations determine the structure of atoms, the chemistry of molecules, and ultimately the properties of matter itself. What we perceive as stable forms, gold, water, oxygen, are nothing more than harmonies of vibrating quantum states. The same principle extends to the nucleus. Inside protons and neutrons, quarks and gluons vibrate with unimaginable intensity, bound by the strong nuclear force. These fundamental entities are not solid chunks but excitations in underlying quantum fields. In fact, modern physics describes particles not as independent objects but as ripples in vast, universal fields. Electrons are vibrations in the electron field, photons are vibrations in the electromagnetic field. The universe is not built of material objects but of resonant waves within invisible oceans of energy. These insights suggest that to ask whether atoms are vibrations is not speculative, it is an accurate description of reality. What we called particles are simply standing waves of energy, stabilized long enough to form the structures of matter. Reality, then, may not be substance at all, but vibration led upon vibration, frequency upon frequency. Beneath the familiar surface of atoms lies a deeper structure, the quantum fields. According to modern physics, every type of particle is linked to its own field that stretches across all of space. These fields are not confined. They are universal, omnipresent, and eternal. When they are calm, nothing is visible. But when they ripple, when they vibrate, particles are born. Imagine the electron field, normally quiet, but when stirred, it gives rise to electrons. The same is true for photons, quarks, neutrinos. Each is a manifestation of vibrations in its respective field. This framework suggests that particles are not fundamental objects at all, but the visible notes of an invisible symphony. Atoms, therefore, are built not of miniature marbles, but of resonances locked into place by patterns of energy. These vibrations are not arbitrary, they follow quantized rules. Just as a guitar string can only produce specific notes depending on its length and tension, quantum fields allow only discrete vibrations. Electrons orbit atoms not in random positions but in quantized energy levels, like chords struck in a precise cosmic harmony. Light is absorbed or emitted only when electrons shift between these vibrational states, producing the spectra that scientists use to read the composition of stars. What emerges is a vision of reality as music, a universe composed of resonant vibrations across hidden fields. Atoms are chords, molecules are harmonies, and matter itself is the melody. Energy, vibration, and resonance are not poetic analogies but literal descriptions of the architecture of the cosmos. And so, the question deepens: if everything we see is the product of these fields vibrating into form, what is it that causes them to vibrate at all? When we picture an atom, it is tempting to imagine it as a miniature solar system, electrons orbiting a dense nucleus like planets circling a star. Yet this image is misleading. In truth, electrons do not orbit in neat paths, they exist in vibrating probability clouds, regions where their presence is more or less likely. These patterns are not arbitrary. They are dictated by the principles of quantum mechanics, where the very identity of matter is locked into vibrational modes. This is why atoms of different elements behave so uniquely. Hydrogen, the simplest atom, carries one electron in a specific vibrational state around its nucleus. Oxygen, heavier and more complex, holds multiple electrons across layered energy levels, each corresponding to a quantized vibration. When these atoms bond to form molecules, it is the resonance of their electron vibrations that determines whether the bond is strong, weak, or impossible. Water, carbon, oxygen, all the substances that give structure to the cosmos, exist because of specific vibrational arrangements in their atoms. Even temperature, something we experience daily, is fundamentally vibrational. Heat is not a substance but the measurement of how intensely atoms vibrate. At low temperatures, atomic vibrations slow, producing solids that appear stable. At high temperatures, vibrations intensify, and matter transitions into liquid or gas, becoming more chaotic. At extreme temperatures, atoms are torn apart altogether, leaving only raw fields of energy. Thus, vibration is not an optional feature of matter, it is the principle that defines it. Atoms are not static units, they are symphonies of motion, sustained in delicate equilibrium by the rules of quantum resonance. Without this vibrational dance, the universe would collapse into silence and void. If vibrations form the skeleton of matter, then light provides the interaction that allows us to perceive it. Photons, the quanta of light, are themselves vibrations of the electromagnetic field. Their existence is deeply tied to atoms, for it is through light that atoms express their energy states. When an electron jumps from one vibrational state to another, it must either absorb or release a photon. This photon carries away the precise amount of energy that distinguishes the two states, no more and no less. It is through these transactions that stars shine, flames burn, and neon glows. The color of light we see is nothing more than the fingerprint of vibrational shifts at the atomic scale. Consider hydrogen, the most abundant element in the cosmos. Its vibrational transitions produce specific wavelengths of light that astronomers detect in the spectra of distant galaxies. These spectral lines are cosmic signatures, revealing the vibrational patterns of atoms trillions of miles away. Through them, we can measure the composition of stars, the expansion of the universe, and even the presence of worlds orbiting other suns. But light does more than reveal vibrations, it reinforces them. Photons can stimulate atoms to resonate in unison, producing coherent light such as lasers. This phenomenon demonstrates that the universe is not random noise, but a network of patterns capable of harmonizing. It shows us that vibrations are not merely abstract, they are communicative, linking atoms through the exchange of energy. In this way, light acts as both messenger and sculptor. It illuminates the hidden architecture of vibrating atoms and binds together the energies that shape the universe. Without photons, vibrations would remain unseen, unheard, and unmeasured. Light is the bridge between invisible resonance and visible reality. Though vibrations begin at the atomic level, their influence extends far beyond the microscopic. Resonance, the synchronization of vibrations, appears across scales, from atoms to galaxies. When vibrations align, they amplify one another, producing structures that are stable, enduring, and sometimes even spectacular. In the atomic world, resonance explains why certain molecules form naturally while others do not. Carbon, for instance, resonates in such versatile ways that it forms the backbone of complex chemistry. The bonds it creates are strong, flexible, and capable of producing enormous chains of atoms. This vibrational versatility is what allows entire planets to form rocks, oceans, and atmospheres. On larger scales, resonance shapes phenomena we might not immediately associate with atoms. Earthquakes, for example, occur when vibrations in the Earth's crust align and release energy in powerful waves. Musical instruments create sound by setting air molecules into synchronized vibration. Even planets resonate. The orbital interactions of Jupiter's moons produce rhythmic gravitational patterns, preventing chaos and sustaining harmony across millions of kilometers. At the cosmic level, resonance becomes even more profound. Astronomers have detected vibrations in the very fabric of space itself, ripples known as gravitational waves. Generated by the collision of massive black holes or neutron stars, these waves stretch and compress spacetime as they travel. Their discovery proves that the universe is not static but dynamic, vibrating even at its most fundamental scale. The principle is clear: resonance is not confined to the atom but is woven throughout the cosmos. From the smallest particles to the curvature of spacetime, vibrations guide the rhythm of existence. Atoms are not isolated dancers but participants in a grand cosmic symphony, their frequencies merging into patterns that span the entire universe. Atoms are often pictured as electrons surrounding a nucleus, but what lies within that central core is far stranger. The nucleus is not a silent sphere, it is a storm of vibrations at scales far beyond ordinary imagination. Protons and neutrons, though seemingly solid, are themselves built from smaller constituents, quarks. These quarks are bound together by gluons, the carriers of the strong nuclear force, in a ceaseless exchange of energy. The interactions between quarks and gluons are not static, they are dynamic pulses, flickering in and out, vibrating within the nucleus. Quarks are not stationary, they are restless, confined within protons and neutrons by the immense strength of the strong force. In this tiny realm, the vibration is so intense that the majority of the mass of the proton does not come from the quarks themselves but from the energy of their constant motion. This realization is profound. Mass, something we assume to be substance, emerges not from solid particles but from vibrational energy. The rest energy of a proton, the weight of matter itself, is born from the ceaseless activity of confined quarks and gluons. Thus, even the core of the atom is not matter in any traditional sense, but a storm of vibration stabilized into form. When nuclei bind together in fusion, as in the heart of stars, their vibrational energy is unleashed, producing the light and heat that sustain galaxies. These processes remind us that the ultimate power of the cosmos lies in vibration, not in solidity. Atoms endure, stars shine, and galaxies burn because vibration is the hidden engine that drives reality from within. The universe operates with rules so precise that even its smallest vibrations follow mathematical laws. One of the most elegant discoveries in modern physics is the relationship between vibration and symmetry. Symmetry is not merely aesthetic, it is structural, determining how particles and fields behave. Quantum field theory describes the universe as a network of symmetries. Particles exist because fields vibrate in ways that respect these symmetries, and the forces of nature, electromagnetism, the strong and weak nuclear forces, are themselves governed by symmetrical patterns. If these symmetries were different, the vibrations of atoms would shift, and matter as we know it would not exist. Take, for instance, the Higgs field. It vibrates in a way that breaks a particular symmetry of the early universe, giving particles mass. Without this vibrational imbalance, electrons would not cling to nuclei, chemistry would not unfold, and stars could never ignite. What we call existence hinges on how vibrational symmetries are arranged at the deepest levels of reality. Even time and space themselves exhibit vibrational symmetry. Relativity reveals that the fabric of spacetime is flexible, stretching and compressing in response to energy. The laws that govern this elasticity are symmetries written into the structure of the cosmos itself. When these symmetries are disturbed, they produce ripples, gravitational waves that carry the vibrations of colossal events across billions of light-years. In this framework, atoms are not just random vibrations. They are the precise, symmetrical resonances that make the universe stable. Symmetry acts as the sheet music, and vibration as the melody, together orchestrating the reality we observe. The dance of atoms extends beyond their isolated forms. When they meet, their vibrations determine how they combine, repel, or transform. Chemistry, at its heart, is the study of vibrational resonance between atoms and molecules. Electrons play the central role here. Their wave-like nature means that when atoms approach one another, their electron vibrations overlap. If these vibrations align harmoniously, atoms bond, creating molecules. If they clash, repulsion prevents them from merging. The very structure of DNA, the spiral of proteins, and the crystalline beauty of minerals, all are products of vibrational alignment at the quantum level. Infrared spectroscopy offers a window into this truth. When molecules are exposed to infrared light, they absorb energy at specific frequencies, causing their bonds to vibrate more intensely. Each molecule resonates with its own distinct vibrational signature, allowing scientists to identify substances by the frequencies they absorb. This technique demonstrates that molecules are not static, they are living resonators, trembling with unique patterns of energy. Vibrations also dictate reactions. Heat, as vibrational energy, provides atoms with the motion necessary to break old bonds and form new ones. Catalysts function by lowering the vibrational threshold required for reactions, guiding molecules into alignment more efficiently. Without these vibrational rules, chemistry would be chaotic, and the complexity of matter would never emerge. In truth, chemistry is the art of vibration. Every bond, every reaction, every structure is written in the language of oscillations. Atoms may appear small, but their resonances shape the vast architecture of planets, oceans, and even the living networks of life itself. Temperature is one of the most tangible ways we encounter vibration. Every material, every atom, carries within it a restless motion. At absolute zero, the lowest temperature possible, atomic vibrations slow to their minimum state. Yet even then, they never truly stop. Quantum mechanics forbids complete stillness. This baseline motion is called zero-point energy, a constant reminder that the universe cannot be stripped of its vibrations. As temperature rises, atoms vibrate more intensely. In solids, they shake in place, bound by their crystalline structures. In liquids, vibrations become energetic enough to let atoms slip past one another, giving rise to fluidity. In gases, vibrations are so vigorous that atoms break free, rushing into open space. At extreme temperatures, as in the cores of stars, atomic vibrations grow violent enough to strip electrons away, creating plasma, the most common state of matter in the universe. Even the colors we see are linked to vibrational energy. A heated piece of iron glows red, then orange, then white, as its atoms radiate photons of higher and higher frequencies. Stars follow the same principle. Cooler stars shine red, hotter ones burn white or blue, all because of the intensity of atomic vibrations. Temperature is not just a measure of heat, it is the pulse of existence. It dictates the behavior of matter, the glow of stars, the movement of galaxies, and even the habitability of planets. The story of temperature is the story of vibration translated into energy scales we can feel and see. At its heart lies a profound truth: warmth, cold, fire, and ice are all the language of atoms in motion. While atomic vibrations operate in the invisible world of quantum mechanics, their echoes can be felt on scales accessible to us: sound. Sound waves are pressure vibrations traveling through matter, air, water, even rock. They are the direct translation of microscopic vibrations into macroscopic patterns. When a guitar string is plucked, its vibration pushes against surrounding air molecules, creating oscillating waves that ripple outward. These waves strike the eardrum, which translates them back into vibration, allowing us to perceive them as sound. In this way, every melody, every spoken word, is a direct expression of atomic motion scaled up into our sensory realm. But sound does more than entertain, it reveals hidden structures. Seismologists listen to the vibrational language of the Earth to detect earthquakes and study its inner layers. Astronomers study vibrations in plasma on the surface of the Sun, translating them into sound-like patterns to probe its interior. Even entire galaxies emit vibrations in the form of waves, though far below the range of human hearing, that encode the dynamics of cosmic evolution. In laboratories, scientists have learned to manipulate matter using sound. Ultrasonic vibrations can levitate objects, guide chemical reactions, or even break kidney stones inside the body. These feats show that vibration is not just a background feature of the universe, it is a force that can be harnessed, shaping matter at scales large and small. Sound is proof that vibration is universal. From the thrum of strings to the rumble of tectonic plates, it demonstrates how resonance bridges the gap between the atomic and the cosmic. It is the voice of vibration made audible. Beyond matter, beyond atoms, even the fabric of space vibrates. General relativity tells us that spacetime is not rigid but elastic, bending and flexing in response to mass and energy. When colossal objects like black holes or neutron stars collide, their violent interactions send ripples across the cosmos. These ripples are gravitational waves, vibrations in spacetime itself. For decades, these waves were theoretical. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected them for the first time. Two black holes, spiraling together over 1 billion light-years away, merged, releasing a surge of energy that vibrated space-time. The signal reached Earth as an almost imperceptible tremor, stretching and compressing reality by less than the width of a proton. Yet this tiny vibration confirmed one of the most astonishing truths: the universe itself quivers like a vast, cosmic drum. Gravitational waves carry unique information. Unlike light, which can be scattered or absorbed, these vibrations travel unhindered across space and time, bearing direct imprints of their violent origins. They allow us to listen to the universe in a way entirely new, hearing the deep bass notes of merging black holes or the faint whispers of neutron star collisions. The existence of gravitational waves proves that vibration transcends matter. It is not confined to atoms or particles, it is embedded in the very structure of reality. Space is not an empty stage upon which matter performs, it is an active participant in the universal symphony, resonating with events that reshape galaxies and echo through eternity. When most people think of empty space, they imagine a silent void. Yet physics reveals that even the emptiest vacuum is alive with vibrations. This restless activity is called zero-point energy. It is the baseline energy that remains even when all classical motion has been removed. In other words, even when you strip away all heat, all light, and all particles, the universe still vibrates. This strange concept arises from the uncertainty principle of quantum mechanics. No particle can be completely at rest, position and momentum can never both be known with perfect precision. As a result, fields that fill space cannot be perfectly still either. They fluctuate, producing fleeting vibrations that manifest as virtual particles, which flicker into existence and vanish almost instantly. Though invisible, these vibrations have measurable effects. The Casimir effect, for instance, demonstrates how zero-point vibrations can generate force. When two metal plates are placed extremely close together in a vacuum, the quantum vibrations outside the plates outnumber those between them, pushing the plates together. What appears as empty space becomes a dynamic sea of pressure created by quantum fluctuations. Some physicists speculate that zero-point vibrations could hold the key to understanding dark energy, the mysterious force accelerating the expansion of the universe. If the vacuum itself is never empty, then perhaps its hidden vibrations supply the energy that drives cosmic expansion. The lesson is clear: emptiness is an illusion. Space itself hums with vibrational energy, a hidden ocean that underpins all existence. Atoms may be visible islands, but the sea of zero-point vibrations is the invisible tide upon which the cosmos floats. Stars are colossal engines of vibration, their energy born from nuclear fusion deep within their cores. In these fiery interiors, hydrogen nuclei vibrate so violently that they overcome their natural repulsion and fuse into helium. This process releases vast amounts of energy, producing the light and heat that sustain galaxies. But the vibrational story does not end there. Stars themselves oscillate like musical instruments, their surfaces quivering with waves of energy. These vibrations, known as stellar oscillations, ripple through their plasma, changing brightness and surface patterns in subtle but detectable ways. Astronomers study them through a field called astroseismology, which allows them to peer into the hidden interiors of stars. Each star produces a unique vibrational signature, like a fingerprint in light. The Sun, for example, rings with acoustic waves that bounce within its layers, providing insight into its temperature, density, and rotation. By analyzing these vibrations, scientists can map the invisible structures hidden beneath a star's surface, much like doctors use ultrasound to look inside the human body. The life cycle of stars is also defined by vibration. In red giants, the balance between gravity and fusion falters, producing new patterns of oscillation before they collapse or explode. In supernovae, vibrations reach cataclysmic levels, blasting matter across galaxies and seeding space with heavy elements. Even neutron stars, the dense remnants of collapsed stars, vibrate with unimaginable intensity, some spinning hundreds of times per second, producing rhythmic pulses detectable across the cosmos. Stars are not just radiant objects, they are vibrating spheres of plasma, each one a cosmic instrument playing its part in the grand symphony of the universe. On Earth, the role of vibration is revealed vividly in crystals. A crystal's beauty lies not only in its symmetry but in the vibrations of its atomic lattice. Atoms in a crystal are arranged in repeating patterns, and these atoms do not sit still, they vibrate in unison, like dancers moving to a hidden rhythm. These collective vibrations are called phonons. Phonons are not particles in the traditional sense but quantized vibrational modes of a lattice. They explain many properties of crystals, such as their ability to conduct heat or sound. When a crystal is heated, phonons carry vibrational energy through the lattice, transporting heat from one side to the other. In semiconductors, phonons interact with electrons, influencing how electricity flows. The transparency or color of crystals can also be traced back to vibrations. When light enters a crystal, it can couple with phonons, producing new frequencies of light. This interaction creates phenomena like iridescence, where surfaces shimmer with shifting colors, and even the piezoelectric effect, where vibrations within crystals generate electric charge. Quartz watches, for example, rely on the steady vibration of quartz crystals to keep precise time. At an even deeper level, phonons reveal the intimate relationship between vibration and matter. They demonstrate that atoms are never silent, even when locked in seemingly rigid structures. Crystals are not frozen. They are alive with oscillations, resonating with an order that links atomic motion to the macroscopic world. In this way, a diamond sparkling under light or a quartz crystal humming within a circuit are not static objects but intricate resonant systems. They remind us that vibration is not confined to the invisible, it animates the beauty and functionality of the materials all around us. While atoms vibrate on their own, the complexity of vibration multiplies when they bind into molecules. Molecules are not rigid, they twist, stretch, and bend, their bonds pulsing with rhythmic motion. These molecular vibrations are essential to the chemistry that builds planets, oceans, and even living systems. Every bond between atoms behaves like a spring. It can stretch and compress, absorbing and releasing energy in quantized amounts. In water molecules, the bonds between hydrogen and oxygen atoms vibrate in specific ways, producing a spectrum that scientists can detect using infrared light. This spectrum acts as a signature, allowing us to identify water not only on Earth but also in the atmospheres of distant planets and moons. Biological molecules are no exception. Proteins fold into complex structures stabilized by vibrational interactions. DNA, the blueprint of life, resonates with subtle vibrations that influence how it stores and transmits information. Enzymes, the molecular machines that drive life's reactions, often work by guiding vibrations into alignment, lowering the energy required for chemical transformations. In medicine, the study of molecular vibrations has become a powerful tool. Infrared spectroscopy and Raman scattering allow scientists to detect diseases by identifying changes in the vibrational signatures of cells. The technique demonstrates that even health and illness can be read in the language of molecular resonance. From the simplicity of water to the complexity of life, molecular vibrations are the bridge between chemistry and biology. They reveal that the pulse of existence runs not only through stars and galaxies but also through the molecules that form breath, blood, and living tissue. Time itself is deeply linked to vibration. The way we measure it, define it, and understand it depends on oscillations at both atomic and cosmic scales. Modern timekeeping rests upon the vibrations of atoms. Atomic clocks, the most precise instruments ever built, rely on the resonant frequency of cesium atoms. When cesium atoms transition between two specific energy states, they emit radiation at an extraordinarily stable frequency, 9,192,631,770 oscillations per second. This vibration defines the very second, anchoring our calendars, navigation systems, and global communications. But vibration is not only our tool for measuring time, it may also be its essence. According to relativity, time is not absolute but woven with space, stretching and contracting depending on energy and gravity. Vibrations, whether in atoms or gravitational waves, unfold within this flexible fabric, marking its rhythm. Time might be nothing more than our perception of vibrational change, the sequencing of oscillations from one state to another. Cosmic vibrations also keep time. Pulsars, rotating neutron stars, emit beams of radiation at astonishingly regular intervals, like cosmic lighthouses. Some pulsars spin hundreds of times per second, their vibrations so precise they rival atomic clocks. These celestial metronomes provide natural benchmarks for measuring time across the galaxy. Thus, vibration is inseparable from time. It gives us the means to measure it, the rhythm to experience it, and perhaps the very substance from which time emerges. To speak of the ticking of a clock, the heartbeat of a star, or the oscillation of an atom is to describe the same universal truth: time is the story told by vibration. Though atoms and fields vibrate beyond direct perception, our senses are attuned to vibrations in remarkable ways. Sight, sound, and touch, all are translations of vibrational patterns into human experience. Light, for example, is electromagnetic vibration. The colors we perceive are simply different frequencies of photons, with red at the lower end and violet at the higher. Our eyes act as receivers, translating the vibrations of the electromagnetic field into the sensation of vision. What we call color is nothing more than our brain's interpretation of vibrational frequency. Sound is mechanical vibration transmitted through matter. Our ears detect pressure waves in the air, turning them into electrical signals interpreted as music, speech, or noise. The harmonies that stir emotion, the rhythms that move bodies, are direct experiences of vibrational order in the physical world. Even touch is vibrational. When we press against a surface, we are not contacting solid matter but encountering the electromagnetic vibrations of electrons repelling one another. The resistance we feel is the vibrational interaction of energy fields at the atomic scale. Our very awareness is shaped by vibration. Brainwaves, oscillations of electrical activity in neural networks, correspond to states of consciousness. From deep sleep to alert focus, the rhythm of thought itself is measured in hertz. Thus, the reality we experience daily is not separate from the universal vibrations but a translation of them into sensory language. What we see, hear, and feel is the world's resonance rendered into perception. To perceive is to live within vibration, attuned to the frequencies that weave the cosmos. At the smallest imaginable scales, beneath atoms, beneath quarks, beneath even the fields themselves, lies what physicists call the quantum foam. This is the seething undercurrent of spacetime at the Planck scale, where the smooth fabric of reality dissolves into chaos. Here, vibration is not an occasional phenomenon, it is the very texture of existence. In this realm, spacetime itself fluctuates violently, warping and twisting with quantum uncertainty. Tiny, transient wormholes may appear and vanish, particles may emerge and collapse back into nothingness, and the geometry of space is anything but stable. These rapid fluctuations are so extreme that time and space lose their familiar meaning, reduced instead to patterns of vibration. The quantum foam is far beyond direct observation, but theoretical models suggest that it influences the universe we experience. It may generate the zero-point vibrations that fill the vacuum. It may shape the cosmological constant, the mysterious pressure that drives the expansion of the universe. Some theories even propose that particles themselves are long-lived excitations emerging from this restless vibrational sea. If this is true, then atoms, stars, and galaxies are built upon the foundation of quantum foam, stabilized vibrations rising from an ocean of unceasing motion. At the very bottom of reality, the cosmos may be less a structure and more a storm, an infinite cascade of vibrations echoing across the Planck scale. The origins of the cosmos itself may be tied to vibration. According to the prevailing cosmological models, the universe began in a state of unimaginable density and energy. In those first fractions of a second, quantum fluctuations, the tiniest possible vibrations, were stretched across the newborn cosmos during a phase of rapid expansion known as inflation. These initial vibrations left imprints we can still detect today. The cosmic microwave background, the faint afterglow of the Big Bang, is not perfectly uniform. It contains slight variations in temperature and density, ripples that were seeded by quantum vibrations in the earliest moments of time. Over billions of years, gravity amplified these ripples, shaping them into galaxies, stars, and clusters. In this sense, everything we see in the night sky, spiraling galaxies, glowing nebulae, planetary systems, can be traced back to microscopic vibrations from the dawn of creation. The universe itself is the grand echo of its vibrational birth. Some theorists suggest that even before the Big Bang, vibration may have played a role. In certain models of cyclic or bouncing cosmologies, universes rise and fall in endless sequences, with each new beginning sparked by vibrational instabilities in the fabric of space-time. Whether one universe or many, vibration appears not only as a feature of existence but as the very trigger of creation. Thus, when we look back to the beginning of time, we find not silence but resonance. The universe was born from vibrations, and in its ongoing expansion, those vibrations continue to shape the cosmos. When we step back and view vibration across all scales, quantum fields, atoms, molecules, stars, galaxies, and even space-time itself, a pattern emerges. Vibration is not confined to one domain, it is the universal language through which reality expresses itself. In physics, every particle is described as an excitation of a field, a vibrational state stabilized by the laws of symmetry. In chemistry, molecules form and transform through the alignment of vibrational bonds. In biology, life harnesses molecular resonance to store information, transmit signals, and catalyze reactions. In astronomy, stars and galaxies vibrate with energies that illuminate the heavens. Even the void between them is alive with the hum of quantum fluctuations. This universality suggests that vibration is not just a property of matter but the underlying principle of existence. To understand atoms as vibrations of energy is to recognize a unifying theme in science, that structure, motion, and form all emerge from oscillations. Beyond science, vibration resonates with philosophy and metaphor. Ancient tradition spoke of creation arising from sound, of existence born from cosmic resonance. Modern physics, though using different language, converges on a similar idea, that the universe is music, played not on strings or instruments but on the fabric of reality itself. To speak of atoms as vibrations of energy is not poetic exaggeration, it is a precise reflection of what we observe. From the smallest particle to the vastest galaxy, vibration is the rhythm of the cosmos, the universal pattern that sustains all that is. One of the great enigmas of modern physics is dark matter. It neither emits nor absorbs light, making it invisible to our instruments, yet its gravitational pull shapes galaxies and clusters. Could vibration hold the key to understanding this hidden mass of the universe? Some theories propose that dark matter may be composed of particles unlike anything we know, perhaps weakly interacting massive particles, or actions, delicate ripples in quantum fields we have yet to detect. In such models, dark matter is nothing less than vibration itself, oscillations in a field that pervades all of space. Though invisible, these vibrations exert gravitational influence, sculpting the cosmic web. Others imagine that dark matter might reveal itself through resonance. If dark matter particles vibrate at specific frequencies, they could be detected by ultra-sensitive instruments designed to listen for their subtle hums. Experiments around the world now attempt to capture these faint vibrations, searching for signals in radio waves, lasers, or superconducting circuits. What is striking is that even our ignorance of dark matter is framed in terms of vibration. We search for oscillations, resonances, or fields trembling in ways our detectors can measure. If dark matter is ever unveiled, it may not appear as solid substance but as a hidden symphony of vibrations, a reminder that the unseen universe is not empty but alive with motion. If dark matter is strange, dark energy is stranger still. It is the mysterious force accelerating the expansion of the universe, making galaxies rush away from one another faster and faster. Unlike dark matter, it is not clustered around galaxies but spread evenly across space, like an invisible pressure pushing reality apart. Some physicists suspect that dark energy may be tied to the vibrations of the vacuum itself, the zero-point energy that pervades even empty space. If every quantum field is alive with fluctuations, then the cumulative effect could produce a repulsive force on cosmic scales. The universe, in this view, is being expanded by the vibrations of nothingness. The puzzle lies in magnitude. Theoretical predictions of vacuum energy are staggeringly larger than what we observe, off by factors of 10 to the power of 1 squared. Why the vibrations of the vacuum appear so finely balanced remains one of the greatest mysteries in science. Perhaps unknown symmetries cancel most of the vibrational energy, leaving behind only a faint residue that drives cosmic acceleration. Or perhaps dark energy is a new vibrational field entirely, one not yet glimpsed. What matters is that vibration again stands at the center. Whether dark energy arises from the tremble of the vacuum or from unknown oscillations beyond current theories, it reveals that the universe itself evolves under the influence of hidden resonances. Space is not expanding randomly, it is vibrating into new forms of existence. If vibration defines our universe, might it also define others? Some cosmological theories suggest that our universe is only one bubble among many, a member of an infinite multiverse. In such scenarios, vibration may be the common thread linking all possible realities. String theory, one of the most ambitious attempts to unify physics, envisions fundamental particles not as points but as tiny vibrating strings. The mode of vibration determines whether a string appears as an electron, a photon, or a quark. In higher dimensional frameworks, these strings may resonate in ways that generate entirely different universes, each with its own physical laws. Our cosmos, then, could be just one melody in a vast orchestra of vibrating possibilities. The idea of a multiverse also arises from inflationary cosmology. If the rapid expansion of space continues eternally in some regions, it may spawn countless bubble universes, each carrying the imprints of quantum vibrations from its own birth. Some of these bubbles may collapse quickly, others may grow vast and long-lived. Each, however, begins with fluctuations, i.e. vibrations imprinted on the very structure of space-time. Though the multiverse remains speculative, it extends the theme of vibration beyond our cosmic horizon. If true, vibration is not merely the language of atoms, molecules, and galaxies, it is the principle by which universes themselves are born. Our reality may be one resonance among countless others, all echoing in a grand, infinite symphony of creation. If vibration is the essence of matter, mathematics is its script. Every oscillation, every resonance, every frequency can be described with mathematical precision. The sine wave, one of the simplest mathematical forms, underlies sound, light, and quantum motion. Fourier analysis, the decomposition of complex patterns into simple vibrations, shows us that even the most chaotic signals can be understood as sums of waves. In physics, wave equations govern the behavior of quantum particles. Schrödinger's equation, perhaps the most famous of them all, describes how a particle's vibrational wave function evolves in time. This equation is not a metaphor, it is the literal mathematics of vibration, predicting how atoms behave, how electrons bind, and how molecules form. Electromagnetism, too, is described by Maxwell's equations, elegant formulas that explain how electric and magnetic fields vibrate and give rise to light. Einstein's relativity links vibration to geometry, showing how gravitational waves ripple through space-time. Even the abstract structures of group theory, which categorize mathematical symmetries, underpin the vibrational modes of quantum fields. Mathematics not only describes vibration, it reveals its inevitability. Any stable system tends toward oscillation, whether it be an electron cloud, a pendulum, or the orbit of a planet. The language of numbers and equations is simply the formal reflection of a universe that resonates at every level. Thus, mathematics is not an external tool imposed upon nature. It is the very architecture of vibration, the code through which the cosmos sings its eternal song. Human ingenuity has long relied on harnessing vibrations, often without realizing their cosmic significance. From musical instruments to modern electronics, technology thrives by guiding oscillations into controlled forms. Consider radio. At its core, it is the transmission of electromagnetic vibrations. Antennas convert electrical oscillations into waves that travel through the air, only to be captured and translated back into sound or data. The digital world, too, rests upon vibrations. Clocks within computers use crystals that vibrate with remarkable regularity, synchronizing the flow of information across circuits. Lasers, another triumph of modern physics, depend on resonance. Atoms are stimulated to vibrate in unison, emitting photons that march in perfect step. The result is a beam of coherent light, powerful and precise, now used in medicine, communication, and even in measuring gravitational waves. Even energy production rests on vibration. Nuclear reactors harness the vibrational binding of nuclei, releasing immense power when those bonds are disrupted. Solar panels capture photons, the vibrations of the electromagnetic field, and convert them into electrical oscillations that power homes and cities. Looking ahead, future technologies may depend even more deeply on vibration. Quantum computers seek to manipulate vibrational states of atoms and ions, using their oscillations to process information in ways classical machines cannot. Nanotechnology designs molecular resonators capable of building and repairing at atomic scales. What these advances reveal is that progress is not about inventing new principles, it is about mastering vibration. Every device, every machine, is a translation of the universal rhythm into a tool we can wield. Among the most profound mysteries of vibration lies within the mind itself. Consciousness, the spark of awareness, is deeply tied to oscillations in the brain. Neurons communicate through electrical impulses, and when networks of neurons synchronize, they produce brain waves, measurable vibrations that correlate with states of thought and perception. Different frequencies of brain waves correspond to different states of consciousness. Delta waves dominate deep sleep, slow and steady. Theta waves emerge in dreams and meditation, associated with creativity and intuition. Alpha waves accompany relaxation and reflection, while beta waves pulse during focused activity. Gamma waves, the fastest, are linked to heightened awareness and complex cognition. These patterns reveal that consciousness is not static but rhythmic. Awareness flows with the oscillations of neural circuits, as though thought itself were a form of resonance. Some researchers suggest that synchronization between distant regions of the brain allows information to integrate, giving rise to unified experience. Beyond neuroscience, some traditions have long spoken of consciousness in vibrational terms, chants, rhythms, and meditations used as tools to align awareness with hidden frequencies. While science approaches the mystery cautiously, the parallel is striking. Both ancient insight and modern research point to vibration as central to the mind. If atoms, molecules, and stars vibrate, and if thought itself arises from oscillations, then perhaps consciousness is the cosmos becoming aware of its own resonance. In this view, awareness is not separate from the universe, it is one of its higher harmonies. For centuries, healers across cultures have believed that vibration plays a role in health and well-being. Today, modern science is beginning to uncover ways in which resonance interacts with the body, confirming that vibration is not only a cosmic principle but a biological one. Cells themselves resonate. The membranes of living cells carry electrical charges, producing oscillations in the form of tiny bioelectric fields. These vibrations influence how cells communicate, divide, and repair. At larger scales, organs such as the heart and brain emit detectable rhythms that synchronize with the body's overall state. Health, in many respects, is harmony, an orchestra of biological vibrations aligned in balance. Modern medicine has harnessed this understanding in practical ways. Ultrasound uses high-frequency sound vibrations to create images of tissues, diagnose conditions, and even break apart kidney stones without surgery. Magnetic resonance imaging, MRI, employs nuclear vibrations in atoms to map the internal structures of the body with astonishing clarity. Pacemakers regulate the electrical vibrations of the heart, keeping its rhythm steady. Even experimental therapies explore vibration as a means of healing. Certain frequencies of light, sound, or electromagnetic fields are being studied for their ability to influence cellular processes, accelerate bone repair, or reduce pain. While still in their early stages, these approaches hint at a future where medicine tunes the body like an instrument, restoring health by guiding vibrations back into harmony. The body, then, is not separate from the vibrating universe. It is an intricate resonant system, alive with oscillations at every scale. To heal is to restore resonance, to bring the inner music of life back into alignment. Long before science revealed atoms and fields, humans intuited the power of vibration through music. Across every culture, music has been used to express, heal, unite, and elevate. At its foundation, music is organized vibration. Sound waves structured into rhythm, melody, and harmony. When a drum is struck, when a voice sings, or when a string is plucked, vibrations ripple outward, carrying emotional weight far beyond their physical form. These vibrations resonate not only with their molecules but with the human body itself. Studies have shown that music can alter heart rate, brainwaves, and even hormone levels. It can calm anxiety, sharpen focus, or ignite passion. Cultures throughout history have tied music to the cosmos. Ancient Greek philosophers described the music of the spheres, imagining that celestial bodies produced harmonies through their motions. In India, the concept of Nada Brahma, the universe is sound, linked vibration directly to creation. Indigenous traditions worldwide have used drums, chants, and songs to connect with nature, community, and spirit. Modern science validates many of these intuitions. Resonance explains why certain notes feel pleasing together, why harmony emerges from mathematical ratios of frequency, and why dissonance creates tension. Music therapy, now a recognized discipline, uses controlled vibration to promote healing in patients, especially in those suffering from trauma or neurological disorders. Music reminds us that vibration is not only scientific but profoundly human. It bridges the gap between the measurable and the emotional, showing us that resonance is as much about meaning as it is about motion. Our senses, though powerful, capture only a fraction of the universe's vibrations. The electromagnetic spectrum alone spans an enormous range of frequencies, yet our eyes detect only a tiny sliver, from red to violet. Radio waves, microwaves, infrared, ultraviolet, X-rays, and gamma rays are all vibrations beyond our natural vision, though instruments extend our reach. The same limitation applies to sound. Human ears detect frequencies between about 20 and 20,000 Hz, but whales sing in subsonic rumbles below our hearing, while bats and dolphins use ultrasonic chirps far above it. Entire worlds of vibrational communication unfold unnoticed, just beyond our biological range. Even touch is limited. We feel pressure, texture, and vibration only within certain thresholds. Yet machines can detect vibration so subtle they reveal the footsteps of insects or the shifting of tectonic plates deep within the Earth. These boundaries remind us that reality is not limited to what we perceive. Instead, we inhabit a narrow window of vibration, tuned for survival but blind to the greater symphony. Science expands that window, building instruments that reveal hidden resonances, from radio telescopes listening to galaxies to particle accelerators probing the vibrations of quantum fields. The more we extend our perception, the more the universe reveals itself as vibration upon vibration, layers of resonance unfolding at scales we cannot directly sense. What we call reality is but one octave in a boundless spectrum of frequencies. The Earth itself is a resonant body. Beneath its surface, tectonic plates shift, oceans crash, and winds howl, creating vibrations that ripple across the planet. These seismic and atmospheric oscillations reveal that our world is alive with hidden rhythms. Earthquakes are the most dramatic example. When stress builds along faults, it releases in sudden bursts of vibrational energy that travel as seismic waves. These waves ripple through rock, water, and even the planet's core, allowing scientists to map Earth's interior much like doctors use ultrasound. Through vibration, we discovered that Earth has a solid inner core, a liquid outer core, and a mantle in perpetual motion. But earthquakes are only one piece of the Earth's vibrational story. The planet also hums with subtle, continuous oscillations, even when no earthquakes occur. This Earth's hum is produced by the constant interaction of ocean waves, atmosphere, and solid ground. Though imperceptible to human senses, instruments detect these low-frequency vibrations resonating through the crust, creating a planetary rhythm that never stops. Even human activity adds to Earth's resonance. Cities generate vibrational signatures detectable from space, cars, machines, and industry leaving their own oscillatory imprint. The Earth, in essence, carries the collective vibrations of nature and civilization alike. Thus, our planet is not silent but a resonant system, a living drum echoing with both natural and artificial rhythms. From deep tectonic quakes to the faint hum of oceans, Earth reveals itself as a vibrational body suspended in the cosmic symphony. The oceans are vast amplifiers of vibration. Sound travels nearly 5 times faster in water than in air, allowing vibrations to carry across immense distances. Whales communicate with songs that can travel for hundreds of kilometers, their low-frequency calls resonating through entire ocean basins. These songs are not random but structured, evidence that vibration is a universal language even among Earth's creatures. Waves themselves are the most visible expression of oceanic vibration. Energy transferred by wind produces oscillations that travel across the sea, sometimes journeying thousands of kilometers before breaking on distant shores. These wave patterns are a direct translation of atmospheric vibrations into the motion of water. Beneath the surface, the oceans vibrate with their own hidden rhythms. Internal waves, far larger than those at the surface, ripple through layers of differing temperatures and densities. Tides, driven by the gravitational resonance of the Moon and the Sun, create global oscillations that shape coastlines, ecosystems, and climates. The study of these vibrations is not only scientific but vital. Submarines rely on the resonant properties of water for communication and navigation. Climate scientists analyze the vibrations of ocean currents to predict weather patterns and track global warming. Marine biologists listen to the underwater soundscape to monitor ecosystems and the impact of human noise. In every sense, the ocean is a resonant chamber, carrying vibrations that connect life, climate, and geology. It is a reminder that the planet's largest body of water is also one of its deepest sources of resonance. While atoms and planets vibrate, galaxies too reveal rhythmic patterns. These vast collections of stars, dust, and dark matter are not static, they spin, collide, and resonate across cosmic scales. When galaxies merge, they produce gravitational waves, sending vibrations across millions of light-years. These collisions often trigger bursts of star formation, igniting entire regions with new light. The process resembles two notes struck together, producing harmonics that reshape the cosmic melody. Even isolated galaxies hum with vibrational order. Spiral galaxies exhibit density waves, patterns of stars and gas that circle like standing waves on a drumhead. These waves maintain the spiral arms we see in stunning photographs, guiding stars into resonant formations that persist for billions of years. Clusters of galaxies resonate as well. Bound together by dark matter and gravity, they oscillate around shared centers of mass, their motions recorded in the cosmic microwave background as faint imprints of sound-like waves from the early universe. These baryon acoustic oscillations are fossilized vibrations from the dawn of time, stretched across billions of light-years. On the grandest scales, even the cosmic web itself, the network of galaxies spanning the universe, emerges from resonance. The filaments and voids we observe today grew from quantum vibrations amplified into structures of unimaginable size. Thus, galaxies and the universe at large are not silent expanses but orchestras of vibration. Their motions, collisions, and waves compose a cosmic symphony that echoes across the void, reminding us that resonance transcends scale, shaping both the smallest atom and the largest cluster of galaxies. Black holes, the most mysterious objects in the cosmos, are often thought of as silent voids, regions from which nothing escapes. Yet even here, vibration leaves its mark. When two black holes collide, they send out gravitational waves, vibrations in spacetime so immense that they ripple across the universe. These cosmic quakes are among the most powerful vibrational events ever recorded. But black holes vibrate in subtler ways as well. When matter spirals toward the event horizon, it forms an accretion disk that trembles with heat and motion. These vibrations emit high-energy radiation, producing X-rays and gamma rays detectable across vast distances. In this sense, a black hole is not entirely black, it sings through the vibrations of the matter it consumes. Even the event horizon itself may vibrate. Theoretical work suggests that black holes ring like struck bells after being disturbed, emitting a spectrum of gravitational waves called quasi-normal modes. Detecting these vibrations offers a way to probe the mysterious interiors of black holes and test the very limits of general relativity. At the quantum level, black holes may hum with even stranger vibrations. Hawking radiation, particles escaping from the event horizon arises from fluctuations in quantum fields, tiny oscillations amplified by the extreme gravity. If true, then even the darkest corners of the universe shimmer with vibrational energy. Thus, black holes are not silent graves but dynamic resonators. They are cosmic drums, their vibrations echoing across spacetime, revealing secrets about gravity, matter, and the very nature of reality. When stars collapse, sometimes they do not become black holes but neutron stars, dense, vibrating remnants that pack more mass than the Sun into a sphere barely 20 kilometers wide. These extraordinary objects are vibrational machines, their very existence shaped by oscillation. Neutron stars often spin at astonishing speeds, some hundreds of times per second. As they rotate, their magnetic fields whip around, generating beams of radiation that sweep across the cosmos. To distant observers, these pulses appear with such regularity that neutron stars, or pulsars, act as natural cosmic clocks. Their precision rivals atomic clocks on Earth, a testament to the stability of their vibrations. But neutron stars also quake. Starquakes, triggered by shifts in their ultra-dense crusts, release bursts of energy that ripple outward in gravitational waves. These vibrations are so powerful that they briefly outshine entire galaxies. Scientists believe such quakes reveal the exotic states of matter inside neutron stars, where neutrons vibrate in superfluid phases unlike anything found on Earth. Some neutron stars vibrate through collisions. When two of them spiral together and merge, their combined resonance sends shockwaves of gravitational energy across the universe. The detection of one such event in 2017 confirmed that neutron star collisions produce heavy elements like gold and platinum, forging them in cosmic vibrational fire. Neutron stars remind us that vibration is not confined to fragile atoms or delicate molecules, it shapes the destiny of colossal stellar remnants, resonating in ways that define the chemical richness of the cosmos. The universe itself is expanding, galaxies receding from one another as space stretches. This expansion is not uniform, it carries the imprint of vibrations that began at the dawn of time. The cosmic microwave background, the faint afterglow of the Big Bang, reveals these ancient oscillations. Its tiny fluctuations in temperature are fossilized vibrations, remnants of sound waves that once rippled through the hot plasma of the early universe. These primordial vibrations acted like seeds, growing into galaxies, clusters, and cosmic filaments. Without them, matter would have remained evenly distributed, and no stars or planets would ever have formed. The expansion we observe today is, in a sense, the ongoing echo of those first resonances. The accelerating expansion, driven by dark energy, may also be described in vibrational terms. If space is filled with quantum fields trembling with zero-point energy, then the universe's growth is powered by the restless hum of the vacuum itself. Expansion, then, is not a silent drift but a vibrational unfolding, as space resonates with hidden frequencies that shape its destiny. On even larger scales, cosmologists speculate that the expansion might not be eternal. Some models suggest the universe could oscillate, expanding and contracting in cycles like a cosmic heartbeat. If true, then even the universe as a whole is not linear but vibrational, its story a rhythm spanning unimaginable epochs. Thus, the expansion of the cosmos is not random motion. It is the ultimate resonance, the vibration of space itself carrying forward the echoes of creation. At the frontier of theoretical physics lies one of the most ambitious ideas ever proposed, string theory. Instead of viewing particles as point-like dots, string theory imagines them as tiny, one-dimensional filaments vibrating at specific frequencies. These strings are unimaginably small, perhaps a millionth of a billionth the size of an atom, but their oscillations could determine everything we observe in the universe. According to the theory, the electron, the photon, the quark, every particle we know, are simply different vibrational modes of these strings. Much like how a violin string can produce multiple notes depending on how it vibrates, fundamental strings resonate in unique ways, giving rise to the zoo of particles that form matter and energy. What makes string theory so profound is its unifying vision. Forces like gravity and electromagnetism, matter and light, all emerge from the vibrational states of strings. In higher dimensional versions of the theory, extra spatial dimensions may curl up into intricate shapes, influencing which vibrations are possible. Our universe, in this picture, is a consequence of how these hidden dimensions resonate. Though string theory remains unproven, its beauty lies in its simplicity. Everything is vibration. The smallest strings hum at frequencies that shape atoms, stars, and galaxies. If the theory is true, then the universe is literally music, a cosmic symphony composed on strings stretched across dimensions beyond our perception. If vibration defines particles, could it also define the very dimensions of space? Some theories propose that the universe has more dimensions than the three we perceive. These hidden dimensions may be compact, curled into microscopic shapes that we cannot directly see. Yet they vibrate, and their resonances shape the physical laws we experience. In string theory, these compact dimensions are called Calabi-Yau manifolds. Their complex geometry determines which vibrational patterns strings can produce. A slight change in the structure of these hidden dimensions could alter the masses of particles, the strength of forces, or even the chemistry that makes stars and life possible. This concept suggests that the constants of nature, such as the charge of the electron or the speed of light, are not arbitrary. They may be the result of resonance within hidden dimensions. The laws of physics are, in this view, the music of geometry, vibrations echoing through spaces we cannot directly perceive. Some researchers go further, proposing that entire universes could exist with different vibrational geometries, each producing unique physical laws. Our cosmos, then, is not inevitable but one resonance among many. If so, the fabric of reality is not static but dynamic. Dimensions themselves are instruments, their shapes dictating the notes that play out as matter and energy. What we call physics may be nothing more than the resonance of hidden spaces, a vibrational harmony woven into the structure of existence. To say that atoms are vibrations of energy raises a deeper question: what is energy itself? In physics, energy is not a substance but a property, an ability to do work, to cause change. Yet it often manifests as vibration. Kinetic energy is motion, atoms vibrating with speed. Thermal energy is the collective intensity of countless vibrations. Electromagnetic energy is the oscillation of electric and magnetic fields. Even potential energy, stored in systems awaiting release, is bound up in vibrational tension, like a plucked string waiting to resonate. On the quantum scale, energy is quantized, it comes in discrete packets linked to frequency. Planck's relation, one of the most fundamental equations of physics, tells us that the energy of a photon is proportional to its frequency of vibration. Higher vibrations mean higher energy, whether in light, sound, or quantum fields. This connection reveals that energy and vibration are inseparable. Energy is not something atoms have, it is the vibration they are. To vibrate is to carry energy, and to carry energy is to vibrate. In the end, energy is the currency of the cosmos, and vibration is its language. From the heat of a flame to the glow of a galaxy, from the hum of atoms to the stretch of spacetime, all energy reveals itself through oscillation. To understand vibration is to understand energy, and to see that the two are not separate but one and the same. Among the strangest phenomena in quantum mechanics is entanglement, the mysterious link between particles separated by vast distances. When two particles become entangled, their states vibrate in harmony, no matter how far apart they travel. A change in one is instantly reflected in the other, as though they share a resonance beyond space and time. This vibrational harmony defies classical intuition. Einstein called it spooky action at a distance, but experiments have confirmed it repeatedly. Entangled photons, electrons, and even larger systems exhibit correlations that cannot be explained by chance. The underlying mechanism remains hidden, but many physicists describe it as a form of resonance in the quantum field. A vibrational coherence that transcends location. Entanglement is not just a curiosity, it has practical implications. Quantum computers rely on entangled states to process information in ways classical computers cannot. Quantum cryptography uses entangled vibrations to create unbreakable codes, protected by the laws of physics themselves. At a deeper level, entanglement suggests that vibration connects the universe in ways we do not yet fully grasp. Particles do not exist in isolation, they are notes in a shared symphony, their resonances interwoven into a single composition. The harmony of entanglement may be a hint that beneath the apparent separations of space and matter lies a unified vibrational fabric, binding all things together. Closely related to entanglement is the concept of quantum coherence. When particles or systems vibrate in perfect synchrony, their wave functions overlap, creating states of extraordinary stability and order. Coherence is the key to phenomena such as superconductivity and superfluidity, where matter behaves in ways that defy classical expectations. In a superconductor, electrons pair up and vibrate coherently through a lattice, moving without resistance. This vibrational harmony allows currents to flow indefinitely without energy loss, a property with enormous potential for technology. In superfluids, atoms resonate in unison, flowing without friction and climbing walls as though gravity no longer applies. Coherence shows us that vibration is not always chaotic, it can be perfectly ordered, producing states of matter that reveal hidden symmetries of the quantum world. Even in biological systems, evidence of quantum coherence has emerged. Photosynthetic complexes in plants, for example, appear to use vibrational coherence to transfer energy with near-perfect efficiency, guiding photons toward chemical reactions that sustain life. These discoveries hint that coherence may be widespread, not a rare anomaly. The universe may naturally favor states where vibrations align, producing emergent properties greater than the sum of their parts. Coherence transforms vibration from noise into harmony, and from harmony into new realities of matter and energy. Time, as we experience it, flows in one direction, from past to future. Yet the fundamental laws of physics are mostly time-symmetric. They allow processes to run forward or backward. Why, then, does time feel irreversible? Vibrations may hold part of the answer. Entropy, the measure of disorder, is deeply tied to vibration. In closed systems, vibrations spread and randomize, dispersing energy into less organized forms. A hot cup of tea cools as its molecular vibrations spread into the air, but the reverse, random air vibrations spontaneously concentrating to heat the tea, never occurs. This one-way dispersal of vibrational energy defines the arrow of time. At the quantum scale, vibrations can remain reversible, as in coherent systems. But as vibrations interact with larger environments, coherence breaks down, producing irreversibility. This process, called decoherence, is what gives rise to classical reality. In essence, the flow of time emerges from vibrations losing harmony, scattering into disorder. Even the expansion of the universe carries this imprint. The primordial vibrations that once rippled through the early cosmos now stretch into larger and colder patterns, embedding entropy into the very fabric of space. The arrow of time is, therefore, the echo of vibration moving from order to chaos. To ask why time flows is to ask why vibrations disperse. The answer may be that vibration itself, in its drive toward balance, creates the irreversible rhythm we call time. The stability of the universe rests upon a delicate balance of forces, each expressed through vibration. The electromagnetic force binds electrons to nuclei, their oscillations giving shape to atoms. The strong nuclear force vibrates within protons and neutrons, holding quarks together in ceaseless motion. The weak force, subtle and elusive, governs vibrational shifts that allow particles to decay, fueling processes like the burning of stars. Gravity, though weakest, resonates across cosmic scales, orchestrating the dance of planets, stars, and galaxies. Each force reveals itself as a vibrational pattern in its respective field. Photons, carriers of the electromagnetic force, are oscillations of electric and magnetic fields. Gluons, mediators of the strong force, transmit the vibrational binding of quarks. Even the graviton, a hypothetical particle of gravity, is conceived as a vibrational ripple in spacetime. This framework suggests that the forces themselves are not separate entities but harmonies within a larger symphony. Where vibrations align, stable matter forms. Where they falter, instability and decay occur. The very architecture of the universe, from the tiniest nucleus to the largest galaxy cluster, depends on the balance of these vibrational forces. Thus, the cosmos is not held together by static threads but by dynamic oscillations, forever in motion. Matter is the chord, energy the rhythm, and the forces of nature the instruments, all blending into a resonant whole that sustains existence. One of the most counterintuitive phenomena in physics is quantum tunneling, the ability of particles to cross barriers they seemingly should not. At its heart, tunneling is a story of vibration. Particles like electrons are not fixed points but wave functions, vibrating across space. When they encounter a barrier, their vibrations do not abruptly stop, they extend as probabilities into the forbidden region. If the barrier is thin enough, the vibrations can carry through, allowing the particle to appear on the other side as though it had tunneled through solid matter. This vibrational phenomenon has profound consequences. In stars, tunneling allows hydrogen nuclei to overcome their natural repulsion and fuse, releasing the energy that powers the cosmos. Without tunneling, nuclear fusion would be impossible, and the universe would remain dark and lifeless. On Earth, tunneling drives technologies like the tunnel diode and the scanning tunneling microscope, which can image individual atoms by detecting their vibrational leakage across barriers. Even biological systems may exploit tunneling. Some enzymes appear to use vibrational tunneling to accelerate chemical reactions essential to life. Quantum tunneling shows us that vibration transcends classical limits. Particles are not constrained by walls but resonate across them, revealing that reality is less rigid and more wave-like than intuition suggests. Matter itself exists because vibration finds paths where none should exist. Not all vibrations are orderly. In many systems, oscillations amplify unpredictably, producing chaotic motion that seems random yet follows hidden patterns. Chaos theory studies these vibrational systems, revealing how small changes can cascade into vast, unpredictable outcomes. Consider a simple pendulum. With small swings, its vibrations are regular and predictable. But when energy increases or when multiple pendulums are linked, the system becomes chaotic, its vibrations never repeating exactly. Despite the apparent disorder, chaos follows mathematical rules, fractals and strange attractors, that reveal an underlying vibrational structure. In weather systems, chaotic vibrations manifest as turbulence in the atmosphere. The flutter of a butterfly's wings may alter air currents just enough to shift a storm's path weeks later. In astronomy, chaotic resonances shape planetary orbits, sometimes ejecting moons or asteroids into entirely new trajectories. Even within biology, chaotic vibrations play a role. The firing of neurons in the brain exhibits chaotic patterns, creating the complexity necessary for thought, memory, and creativity. Heart rhythms, normally steady, can slip into chaotic oscillations that endanger life, reminding us that harmony and chaos exist side by side. Chaos demonstrates that vibration does not always produce symmetry and order. Sometimes it gives rise to unpredictability, richness, and diversity. The universe balances between harmony and chaos, and in this balance, complexity is born. As we trace vibration from the smallest particles to the largest structures of the cosmos, a unifying theme emerges: everything is connected through oscillation. Atoms are not fixed entities but resonances in quantum fields. Molecules bind through shared vibrations. Stars and galaxies shine because of vibrational energy released in their cores. Even space and time themselves ripple with gravitational waves. This unity suggests that vibration is not a property within the universe, it is the principle that is the universe. Matter, energy, forces, and dimensions all reduce to oscillations in underlying fields. The cosmos is less a machine of separate parts and more a symphony of frequencies woven together in infinite complexity. When we speak of atoms as vibrations of energy, we are not speaking metaphorically but scientifically. Particles are excitations, ripples, waves in invisible seas of energy that stretch across all of reality. From quantum foam to galaxies, vibration is the common thread linking every scale of existence. This realization also reshapes our perspective. Solidity is illusion, permanence is vibration sustained. What we call things are temporary harmonies, frequencies held in balance before shifting into new forms. The universe is alive with motion, a continuous transformation where nothing is static and everything resonates. To see atoms as vibrations is to see the universe not as matter but as music, a cosmic resonance that composes itself endlessly, across scales too vast and too small for us to fully grasp. And so, we arrive at the end of our journey. From the trembling of quarks in atomic nuclei to the ripples of spacetime across billions of light-years, vibration has revealed itself as the hidden engine of existence. Atoms are not static beads of matter but standing waves, resonant expressions of energy woven into patterns of astonishing complexity. Every star that burns, every ocean wave that crashes, every breath that moves through a living body, all are vibrations echoing from the first resonances at the dawn of time. The universe itself was born in vibration, its earliest quantum fluctuations stretched into the grand structures of galaxies and clusters. The music of creation still plays, and we are part of its song. Science shows us that vibration is more than analogy, it is truth. Particles are excitations of fields, and reality is their resonance. Yet beyond the mathematics and the theories lies a profound wonder. To exist is to vibrate, to participate in the eternal rhythm of the cosmos. The question, are atoms just vibrations of energy, finds its answer here. Yes, atoms, molecules, stars, and galaxies are all resonances, sustained harmonies within infinite fields. But in recognizing this, we uncover something deeper, that the universe itself is not made of things, but of frequencies. We are immersed in a cosmic symphony, and every atom is a note in its infinite score. And so, as the vibrations continue, so too does the story of the universe. For the resonance never ends. It only changes form, weaving new harmonies from the energy that has always been and always will be.